in various directions of applied probability. For the last several years, he became very in energy systems and so on. He is also well known, to me, he is well known as a co-author of late Richard Curidi, and this is the celebrated book on Markov chain stochastic stability, which had how many, 5, 6 editions, I don't know, hundreds of them. Anyway, so.
Thank you, sir. Great. Yes, it's of course it's an honor to be here. Actually, it's almost exactly 3 years ago that I had the honor of standing. Oh yes, I'm supposed to turn the mic on. Great. It was almost exactly 3 years ago that I had the honor of standing here and presenting a related talk. And actually, it was just from the interactions, it actually brought me back into this area. So, in fact, I mean, my original work in this area was with In-Koo Cho actually more than 10 years ago, on trying to understand the California power crisis. And it took us 6 years to get our first paper published, just because it's such a, energy is a very, I think that it's a wild area because there's such a diversity of problems, and such a difficulty in communication because of the different, there's a different language in each area. And then try to work with a lot of people. I mean, the oldest is In-Koo Cho, an economist at Illinois, and most recent is Anna Bushitz, who's at INRIA, and I'll mention just briefly some of the work there. So this is not meant to be ironic, how economics can help us. There's ways in which economics can help us a lot, and there's ways in which economics has really interfered with the process in the past. And so I'm going to try to explain that in this lecture. And so you can imagine the problem. I've got an hour, and I'm going to try to give an overview of the control issues in the grid. And I'm going to try to give an overview of some of the economic problems I see. And then I'm going to try to explain how I see how we could fix it. And to do that in an hour is impossible. So I'm going to do this. I'll do this with images and just try to inspire you to read the papers, okay? But before I do that, I want to inspire you to come and visit me. I've just moved to Florida. And most of you have this crass image of Florida as malls and Disneyland and nothing else. But one big reason I moved to Gainesville was this. 45 minutes from my house is the Suwannee River that empties into the Gulf of Mexico. And yes, over there, those are manatees swimming by, and dolphins jump out of the water. And there's my friend, my co-author, Prashant Mehta, with his first encounter with a baby manatee at about 150 kilos. And in there, the egrets and herons, it's just a beautiful place. So, if you want to visit Gainesville, even if you don't want to talk to me, just let me know. Okay. So first, I want to start with a short quiz, and I think that I don't even need to say anything more in a way. I mean, once you take this quiz and see the answers at the end, you'll see my point. Where economics is really valuable, where control is needed. Basically, what are the roles of the different players, at least on the academic side, and also the players that, who are building the grid. So the big thing is that the value of power, and this is a quiz about the value of power. Of course, it depends on location and context. When I'm sound asleep, I don't care at all. And these are prices in the Midwest ISO, the balancing authority in the Midwestern U.S., and these are prices that are very high. Believe it or not, $62 a megawatt hour in the U.S. is double what you'd expect, typically. And it's over here, it's lower. It's only $20, and then here it's higher. But this is a joke. It gets much more extreme than that. Okay, so this is the quiz. So here is a little typical plot of the wind generation in the entire Pacific Northwest. And you see it goes up to almost 4 gigawatts and then back down. And the average here is about 1.6 gigawatts. And the average price is about $20 a megawatt hour. In fact, this whole time, it's $20 a megawatt hour. So what's the value of this chunk of power? And the answer you'd guess would be over a day. Well, it's 60. That should be megawatt hours. Sorry, it's a typo. It's 1,600 megawatt hours times 24 hours, and times $20 a megawatt hour. If I've done my algebra correctly, it should be $750 million. Okay, so true or false? Okay, and a short yes or no at the end, okay? So, I mean, anyway, submit your answers at the end. So what about this? So if we agree with that the average of this is 1.6 gigawatts, and therefore the value is $750 million, then you'd agree with this. This is a signal that somebody's putting in power, taking it out, putting in power, taking it out, over and over again. So they do nothing. You average this, you get 0. So the value is 0. Right? So, all right. So to write down your answers as we go along. Don't do it now. Wait about halfway through. And you think you know what I'm thinking, but you're wrong. Each case is an obvious answer. And I think you think I'm choosing one of them, but I'm going to show you wrong. Okay, so I'm just trying to get you going. So answers to be submitted at the end. Okay, so I want to give the conclusions in advance. So I want to make sure they're not missing. Okay, so the first thing is that there's a long-term problem of the fact that fossil fuels will be gone for our great-grandchildren. Panda bears and polar bears as well, probably. And there's going to be a huge change in the world over the next century. And so there's a long-term issue that, of course, control theorists and economists, we all forget, and policymakers forget. So it's sad. I mean, so I'll start with a depressing note. It's just a fact of life. So we need renewable energy to slow this down. And so we need an energy infrastructure. Okay? So sticking a bunch of wind farms in the Pacific Northwest is not the answer. We need a lot more than that. I mean, put it simply, the energy policy in the U.S., having incentives for wind farms and nothing else, would be like having incentives for cars at the end of the 1800s and no incentives for building roads. Cars would be worthless without roads. And wind farms are becoming worthless because there's no infrastructure. It's exactly analogous. So here are the elements. So first of all, the big point here is that electricity has been considered as a commodity. And this has been going on ever since Fred Schweppe's book on spot pricing. That basically thinking of electricity like flour or rice, that it's interchangeable. And you can imagine what I'm thinking. That quiz is all about this. The value of those different trajectories are very different. It's nothing like a commodity. There's services. Gas turbine generation provides regulation services. HVAC stands for heating, ventilation, and air conditioning. And as Ivana pointed out, in the Shetland Islands, by ramping up and down the heating and ventilation, you can provide a service to the grid. That's a zero-mean service. These smart grid programs have created this, framework for us. I mean, some infrastructure, very little, and the real-time control is going to be an essential way to combat volatility and ensure reliability. Making use of these resources. But another big point is that real-time prices have no value whatsoever. In terms of any kind of goals we'd like to achieve, controlling the grid, incentivizing new products. Think about what economics has been great for. I mean, in the U.S., it's a disaster healthcare, right? Although, on the other hand, the horrible healthcare system is creating incredible innovation. And economists are very proud of that, and rightly so. Competition creates innovation. Now, do real-time prices do that? No way. Do they create incentives for new generation in the right places? There's no empirical evidence. So we keep talking about real-time pricing, but nobody's ever shown why. So Fred Schweppe proposed this in the late 70s, and we've taken it for granted ever since. And I've been asking this question for 10 years, and I've never gotten an answer based on empirical evidence or scientific evidence. So I want to explain why there's no reason for real-time prices and explain alternatives. And you can only understand that within a controlled context, and that's why an hour is very difficult. And that's why I've never really been able to do this. I can explain this to control theorists pretty easily, but to a mixed audience it's harder. Okay, so an outline. It looks horrible, 66 slides, it's all pictures, and so don't worry, it's not that bad. So I want to talk about what are the control issues in the grid, what's happened in the last few years. It's really exciting for me because 3 years ago I gave a talk with some wild disaster stories, and it's gotten much worse. The last 3 years have been chaos. I want to give a little bit of science just to convince you to maybe read a few of my papers that are more on the economic side, and then mainly conclusions and suggestions. All right, so I gave a talk like this in India a month ago, and the slides are perfect for this meeting as well. India is a beautiful, highly connected control system. You've got, here's some nodes. I looked on Google Maps, how long would it take me to drive from Mumbai to Calcutta. It actually tells you that this route would be 66 hours. And so it's very hard to drive around India. But boy, can electricity do it well, So you have some sort of crisis here near the Taj Mahal, and you see, Calcutta and Mumbai, thousands of miles away. They're all oscillating in out of phase, but they're all coupling together. It's just beautiful. India, it's amazing in what they can get away with. The whole system remains stable in spite of these disruptions. And when things don't, keep coupled like that, this is a July 30th blackout last year. You get this lack of synchronization, the whole system comes down. Okay? And this cost a lot of money by Indian standards. Okay, so this talk, I'm not going to talk about India much. I'm going to talk mainly about engineering and U.S. energy policy. Okay, and it's mainly a lot of it, 50% humor. Okay, all right. So basically, electric power grids, of course, we know they're a large, complex system. Everyone knows this. And you can see the kinds of things people worry about. This is the angle contour map in the U.S., so the phase difference of the frequency of electricity in the grid. And things like that, a big transition of phase, really scares people. But measuring phase isn't that easy. So this could be just an artifact of bad estimation. And so reliability is incredibly important. Efficiency, I don't know why I put that in. I couldn't define it. I don't know what efficiency is. No idea. And the environment is incredibly important in operations and planning. So this shocks all the time, from this energy, generators break down and so forth. But the biggest shock is policy. Government mandates for renewables just whack. It's an incredible step response that we've seen in the last years. The projected renewable energy consumption in the U.S. is growing very quickly. You can see since Obama's was put in. And it will grow, although this projection is probably not going to happen because of two reasons. One is that they didn't foresee they needed an infrastructure. They didn't see that you can't just throw a bunch of cars down and not have roads, and now they see it. The other problem is this, fracking. So in the United States, there's been no public discussion on fracking, which is, getting natural gas by setting off little bombs under the ground. There's been no discussion about the potential damage to the water supply or earthquake. There's just a lot of risk that we don't know about. And so it's all been going very quickly, and there's an exponential growth in the amount of, this is billions of cubic feet per day. It's gone to 6 billion cubic feet in 2012 compared to 1 in 2009. And that's made a lot of people, at least in industry, say, forget it. We've got ethical energy here. It's much cleaner than coal. Forget it. And so there's a huge shift in thinking in the last year. Incredible time. So back to this. So anyway, it's got at least what's good about all this crisis is opportunity. I mean, both consulting and academics. So we've got supply and demand being volatile. We all know this. We've got transmission constraints, and these traditional generators have non-convex and dynamic costs. Again, this is incredibly naive. Gas generators, it's all sunk cost. It's $1 billion to build the new gas power plant in Florida. $1 billion, imagine the interest rate on that. It's almost all the sunk cost. The actual running cost is nothing. The marginal cost is just trivial. These dynamic costs, the cost of ramping up and down, that can be costly. So as a control theorist, what do we have? We've got the power grid, and we've got the desires of consumers, suppliers, and all of that. And the output of the system is power consumption, quality of life, which includes environmental factors. And they're disturbances, okay? And the disturbances to the grid are in part because of this volatility that I'm talking about here, that wind, solar are extremely volatile. And we need, in control language, you need some sort of actuator to try to reject these disturbances. So if you sit in an airplane and look out on the wings, you see the flaps going up and down. They're not just exercising, they're reacting to the disturbances, the fact that there's gusts of wind. And so this regulation signal that you'll see here, that BPA needs, that's the gusts of wind. And you need the ailerons to flap up and down to regulate the grid. Okay? And so what are the actuators? What are the ailerons in the grid? Well, there's millions of them. So the traditional ones, we've got hydro, gas, which is fairly controllable. Not as controllable as you think. So 3 years ago, I said, wow, they're so lucky in the Pacific Northwest. They've got hydro. They can just pump it up. They can pump water into the dams if they've got excess. They can dump the water if they want to. It's not true at all. The salmon don't like it. You can't dump the water too quickly, you kill the fish. And so it's not as controllable as you think. You've got capacitor banks, you've got batteries and flywheels, but you've also got flexible manufacturing today. Alcoa gives up some of their authority, allows the utility to ramp up and down the consumption as a regulation means. You've got HVAC that was mentioned. There's a project in Florida as well as the Shetland Islands. You've got brick baking in India. 20%, I heard, of energy in India is from the kilns to bake bricks. Can you imagine anything more flexible than that? And they've got tons of sun. It's volatile, but the demand is incredibly flexible. And water pumping is common. So in California, I always like to joke that when you're in the Colorado River, you see the last drop of water across the Mexican border. The rest of it's pumped over to water the lawns in Beverly Hills. And to water some orange trees as well. But so that water pumping is very flexible. And so that's being done today as a way to regulate the variability in the grid. Okay? But so how do we harness these actuators? That's the question. And will we put this guy in the loop? So this is, do you know who that's Milton Friedman. So, are we going to call the Chicago boys, stick them there, and have real money and consumer response in the loop? But of course not. I just talked about those ailerons in the airplane. It's the same problem. It's a regulation problem. And if you put some uncertainty in those flaps, what's going to happen? It might not crash the plane, but it's not going to be as comfortable a ride. Okay, if you add extra uncertainty, all right. And so there's no way we would do that with this sort of regulation problem. Okay, and that's what I'm talking about. It's a different matter of time scale. So economics is going to be very helpful in certain time scales, but here there's no value whatsoever at all. And I want to prove that point. So this is Peter Kokotovich, who actually he's a wonderful control engineer who worked in energy back in the 90s before the funding got cut for energy research in the U.S. But the control community could solve this problem. I don't think the control problem is that hard. It's incentivizing the resources, and that's where economics is important. Incentivizing the creation of resources. So we need the resources there, and then once we have the resources, the control problem I don't think is that hard. Maybe I can't do it alone. We'll need help from the control community. Has to work together, but I don't think it's any harder than the communications challenges. Before the telecommunications evolution, you had Shannon's theory of information theory was beautiful, but almost worthless. It took a few years for a group of academics to get together and create algebraic coding theory, which was a way of implementing Shannon's beautiful ideas. It just took a few years of creative thinking. Once we have the resources, I know that the communications control communities can nail this, and that's why the biggest challenge is economic, but economic in the sense of getting these resources. Okay. So now's the comedic part, and then I'll get back to some science. So there's a study you should all read, the Energy Information Agency, 2011. There's references at the end of the talk. It basically goes over the last few years and what can we learn by all the smart grid programs and so forth. So millions of smart meters have been installed. There's a PNNL study you should all look at, Pacific Northwest National Lab, where they tried to automate water heaters and found if they automated the consumption of water heaters, they could get some ancillary service, so they could regulate the grid. And these beautiful stories of IBM and Google and Alcoa having contracts with utility companies and balancing authorities to give up some control of their manufacturing so that they could provide reliable ancillary service to mitigate volatility. And it's working. It's working all over the place. But the trouble is, it's inspired in part by this FERC ruling 745, which says that demand response has to be compensated the locational marginal price for energy. Okay? So they think they know the value. They think they've passed the quiz. And I want you to think what their score would be on the quiz. So FERC is the Federal Energy Regulatory Commission, and they're saying this is the price. They know the value of that ancillary service. And this has caused war. I mean, there are lawsuits going on, and for good reason. So the fact of incentivizing Google and IBM to provide ancillary service is a very, very intelligent move. But to dictate the price, for them to say they know the value is incredibly arrogant. Okay, and I say that with no arrogance. This is true. They don't know the value of this. The value of this is very subtle. As I say, you're all going to pass or you're all going to fail the quiz. It's very subtle. Okay, so I'm not going to go through all this. I just want to mention one favorite study, Constellation Energy and New Jersey Power and Light. They gave customers, residential customers, a $50 Walmart gift card and a very small reduction in their rates for power. And all they asked was for small deviations in their water heaters for ancillary service. Everyone was happy. The residential consumers got their $50 Walmart coupon and felt happy. They got a small rate reduction, and the utility company got a little bit of ancillary service. It's not perfect. There's incredible risk to New Jersey Power and Light. That's why I think in a way this was just a public relations ploy, because they don't want to be stuck with a 10-year contract where they might find that batteries are very cheap tomorrow. So contract design here is very subtle. It's not trivial, but there's a successful demonstration. It was perfect, for everybody. The consumers at least are thrilled, and right now they're thrilled. Okay. All right. So I got to mention. So since the Shetland Islands was mentioned, Ivana, I have to mention some work in Florida. So we've got a building we've actually been, my colleague Prabir Baruha mainly, Pugh Hall. It's a building at the University of Florida that we've been taking measurements from for the last 5 years. And basically it's got what's called a PI controller. It's a proportional integral controller. It doesn't matter really the details. But the idea is this: you've got the power grid I showed before, and here's one of the actuators. What you do is we take this regulation signal that you can get from PJM. It's one of the one of the big balancing authorities, if you like. And we basically take that information to the building, and we ask one of our control friends, Bill Perkins here, to help us design some sort of filter. And basically what we're going to do is we're going to band pass that filter, and I'll explain why in a moment, and basically perturb the power consumption in those fans. Up and down, up and down, up and down. Not too fast, because that would destroy the fans. Not too slow, because we'll see. And so that's a lot of ancillary service you can get. So we estimate that with just the commercial buildings in Florida, you could provide the entire, it depends on how you add it up, but let's say the minimum 70% of PJM's regulation signal, and that's like more than half of the U.S. And so Florida could just take care of more than half of the U.S. But there's a fight people talk about between the control system in the building and the control system in the building and our control system. But that's why you have to do this. Anyway, first of all, the reason is that our perturbation seen as a disturbance by the control system in the heating and ventilation and air conditioning. PI is proportional integral control. Okay, so I try to consume less energy, and the PI controller says, well, we got to consume more. There's a fight that is conceivable could happen, but there's a simple solution is to restrict the bandwidth that's seen by the PI control freaks. And the PI controller wants to regulate the system, but only at a low frequency. So you basically just take a certain bandwidth. I'm sorry you can't see this very well, but a bandwidth between 4 seconds and 600 seconds, and just just put the regulation signal through a bandpass filter, and the PI control system, the control system in the building won't see it. It doesn't care about high frequency disturbances, and neither will you. Can you imagine if those fans were reduced 10%, increased 10%, reduced 10%, increased 10%? Do you think you'd feel it? So in the experiments we've done, there's a half a degree fluctuation in temperature, and with a half a degree fluctuation in temperature, you can provide all the ancillary service needs you need. Just Florida for the whole half of the U.S. And this I can't spend much time on at all, but think about Florida. Where does electricity go? It goes for HVAC. Buildings have to be 10 degrees centigrade in the summer. And they have to be, 30 degrees centigrade in the winter, I don't know. But and they've got pools. Everybody has to have a pool, and they have to be cleaned. So there's at least a gigawatt of electricity in pools. And that's beautiful for mitigating lower frequency volatility. And so how do you do that? Well, it's not obvious, and you sure couldn't do it with real-time prices. The prices would get high enough, all the pools would shut off. We went this very carefully to follow this signal to match the volatility in wind. And to do that takes some control design, but it can be done. and it can be done, and actually this is joint work with Anna Buschitz here, but it can be done, and this is preliminary work. I mean, it's going to take some more work, but there's a huge flexible demand there, not as powerful as the kilns in India, but still very valuable. All right. But here's the negative thing. So the failures were all involved real-time prices. I mean, there was not a single success story that I know of in the Energy Information Agency study. And the reasons are that they wanted predictable cost savings, and nobody could guarantee it. Okay? So with the contracts that New Jersey did, there was a guaranteed cost savings. Nobody trusts the utility companies. They don't trust people to tamper with their appliances. And a lot of people thought that the smart meters sent off radiation that would give them brain damage. It happened. People did say that. But the biggest thing is this. The value of ancillary service obtained was reduced because of the uncertainty of level of consumer response. That's not just true of residential consumers. When the New England Balancing Authority did experiments and tried to have auctions, they had auctions for demand response based on prices. They had no idea what they'd get. Vermont would give them twice what they wanted. Maine would give them nothing. And they shut down the program because of the uncertainty alone. And that was not residential customers. So, but last year at the Smart Grid meeting, Terry Boston, who's the CEO of PJM, was screaming that prices to devices are coming our way. And he defined what it meant, that our water heaters would respond to real-time prices. And Dick O'Neill, who's the chief economist at FERC, says this is the only way we can do it. Okay. So my concern is real-time pricing. Time of use is a totally different problem. That's an open-loop issue. It's like the day-ahead planning of an aircraft. Nothing like flapping wings up and down. So time of use pricing, I was really happy to hear in France it does have some value. In England, it doesn't. I mean, England, time of use pricing hasn't been very valuable. For some reason in France it has. And contracts, of course, I think, can be valuable, but it's not trivial to design contracts, but they have a lot of value. And I'm just put this up just to say, often people say nobody really believes this. And I just want to say, yes, they do. I mean, Frank Wallach says the only way to deal with these issues is real-time prices. Borenstein says the same thing. If you look at the definition of demand response on the DOE website, Department of Energy website in the U.S., it's defined as consumer response to prices, and that's a huge mistake. Okay. So just talking about prices again. So as I was preparing the lecture, I gave a version of this in Florida a few weeks ago. As I was preparing the lecture, I saw the prices went to $500 and negative 100 here. I don't know. This was at 7 in the morning. So the normal price is $30 a megawatt hour. It's 500. And it stayed that way for a while, and it went down to it near 0, and then it went up to 30, and then 0. That's negative, by the way, again. They go down to negative 100 or so, and then 0. And a little bit later, negative, you can go as negative as you like. I think they have a negative price cap of $100 or so. It goes down to negative 1,000 is the price cap in Australia. And in New Zealand, they don't allow negative prices. The prices are very often negative, every day. So go to New England any morning, I mean the Midwest, any day you'll see negative prices. And it's just beautiful art. And so this is really high prices. I mean, 10 times at least the average. And this is just me bored, with my talk and looking at the web. And here's beautiful. Isn't that color? It's art. It's absolute art. So that's negative. That's really negative. And then that's $500 minus 100. Okay. And so you can say, well, puts in some transmission. Well, just imagine the lawsuit. Talk about lack of incentive. So this has been going on for years. Imagine politically trying to put a transmission line there. What would happen? These people are making money. You take away their business. So anyway, it's art. So go to the Midwest ISO. It's very pretty. So prices depend on time, location, and context. Prices, not value. Okay. All right. So here's more art. In the winter of 2011, the typical prices in Texas look like this. They average about $30 a megawatt hour, maybe 20. And they went up to the price ceiling of $3,000 a megawatt hour. And that area into that curve is $20 million, $50 million. I have contacts to the DOE. They don't know exactly. But there's a huge amount of money was gained. And it was absolutely a scandal at the time. The Houston Chronicle wrote this beautiful editorial, and they said, who profited from this near meltdown? We still don't know. And what can be done to incentivize power producers to maintain adequate reserve capacity for emergencies? So what happened is the coal generators weren't insulated properly, so they froze. So because they saved money not insulating, they made $20, $30, $40 million. Need I say more? Now, what was the response to this? Now, you know that policy goes very slowly in the US. You've heard the debates about gun control and so forth. Well, some of it goes very quickly. So very quickly they said, well, the solution is to raise the price caps to $9,000 a megawatt hour. So it's $3,000. That was proposed. A few months later, yes, it's done. So basically, that's the efficient outcome, and that's only half ironic. Okay. So of course the generators got what they wanted. they got to make more money the next disaster, and in a sense, actually, this is justified. I can prove that given the economic model that's being used, this would be the right answer. But of course it's ridiculous. I mean, of course it's ridiculous. Nobody could support this without knowing the actual details of this physical system. It doesn't make any sense. So this policy, I don't get it. And anyway, the same year, day-ahead prices also went to $3,000 a megawatt hour because of shortage. All right, New Zealand's the best example ever. So typical prices there are more expensive, maybe an average of $50 in New Zealand a megawatt hour. Well, I don't know the exchange rate. Maybe that's not very much. I don't know. But notice they have a negative price cap. So that would have gone down negative if not. But look at this. Okay, ready? Everybody keep your eyes open. There. See that? They've got a price cap. So they're way ahead of Texas. The area under those two curves I do know. It's $25 million. I wrote there, yeah, $25 million. Okay. Now guess what happened? It was just like in Texas. There was a scandal. There were outrage, and people were horrified. And but the New Zealand Electricity Authority said Genesis, who decided to go Paris in the middle of the day, was not guilty of anything manipulative or deceptive. However, so they didn't do anything wrong. Okay. So there's a bank. $25 million disappears. The guy walked in. The guy walked out. Did nothing wrong. But this guy, the high prices threatened to undermine confidence in and damage the integrity of the market. So to protect the integrity of the market, they took 90% back. So this poor guy walked to the bank and walked out. He still had to give 90% of $25 million back. Now, where did he get the money? So if this happens, what do you do? I mean, if a bank loses $25 million, what do? You get some cameras in there. You find some way to find out, to know if this was manipulative or not. You not say these seem like nice guys. It's amazing. And so they still have the same policy. So this could happen again. So they're just going to trust that they're not going to go Paris in the middle of the day again. Or maybe they'll raise the price cap, and then it'll never happen again. All they need to do is raise that price cap to $40,000, and then there'll be no problem. So the PNNL study was very valuable at the Pacific Northwest National Labs in showing how automation of devices could provide ancillary service, much like the HVAC project. But they had initially, this is just the very first part. I mean, they had a very, they would admit, naive approach. They were taking some marginal cost sort of pricing scheme to regulate those devices. Something like comfort is proportional to price. Roughly speaking. And this is what you got. The prices were just doing what you expect. Price is high, shut down. Price is low, turn on. Up, down, up, down. Just like you'd do if you had people putting in money into a back of an airplane. The flaps go up. You want them to go down. You take your money out. It's just, and they shut it down, and then they realized they needed automation. Okay, and so the joke is this is consumer anger. It just. Okay, so a bit of science. Okay, so again, real-time pricing is what I think is absurd, not time of use. So I want to just give you 3 theorems, and I can't give you all the details, but just one of these has been published, and the rest are in print. But if you take temporal constraints into account, so you take the fact that it takes time to ramp up generation, the grid has the dynamic constraints. This is what I presented here 3 years ago. Price is never marginal cost, but it's marginal value, what any economist would say. So I'm not disagreeing with anybody. But imagine marginal cost of generation. It looks like Texas or New Zealand without the price cap. And so that's why economists are correct, that doesn't make sense. You should have a price cap. Theorem. In a perfect world, in a competitive equilibrium, that means that prices are exogenous, but nobody can influence prices. Okay, in a perfect world, price is marginal cost, and that's a competitive outcome, and the social, it's a social optimal outcome. Okay, in a perfect world. So it's a Lagrangian decomposition to prove this, just like in the standard proof of the second welfare theorem. Basically, you take supply and demand equals demand you use a Lagrange multiplier to relax that. But this is a temporal setting, and there are ramp constraints. So you get a completely different outcome than a standard economics analysis. Price is never marginal cost. And marginal value is not obvious at all. With network constraints, it can go well beyond the way economists typically define marginal value. It can be 10 times that if you want. And it can go negative, as far as negative as you like. Okay. So if you didn't have price caps, Australia would look like an efficient equilibrium. So prices, now there's a price cap of $10,000, and there's a negative price cap of $1,000. If they had allowed that to go to $40,000 and allowed that to go to negative $20,000, this would be consistent with the theory in my paper, in a competitive equilibrium. But there's no such thing as a competitive equilibrium. There's no way. There's no way that you can't, that there isn't market power, that the players can't influence prices. Okay. So the marginal value could be $250,000. Who knows? But here's a second theorem. In this equilibrium, the average price is the average marginal cost. Okay? And the average marginal cost. And the proof of that is by a Lagrangian relaxation of the initial condition, keeping the dynamical system. So the question is, who would stay in this business? If my entire cost is a sunk cost, which is $1 billion, and I'm paying interest on that, and the only thing I'm getting back, is this incredible volatile income, where my average price is my average marginal cost, sunk cost lost, everyone's gone. So really the theorem says there is no equilibrium, everyone's gone, everyone's dead, which was happening in the US before fracking. Natural gas generators were all going out of business. Last result. Now the real issue is the fact that there's a cost to ramping up and down. So it's much cheaper to provide gas generation from gas turbine generators at a constant rate than ramping up and down, up and down, up and down. And it's roughly quadratic, perhaps. Oh, wait a second. I'm sorry. I jumped ahead of myself. I wanted to give you a success story first. So this is a regulation signal required by the Midwest ISO. And I just wanted to give you some motivation first. So FERC, the Federal Energy Regulatory Commission, has now mandated that balancing authorities pay for this high-frequency regulation service. And they're much better on this. They don't say how to do it. Okay? So the Midwest ISO decided to come up with this very eccentric sort of measure of value. It's not really continuous time, it's discrete time. But they basically take the absolute value of the derivative in discrete time and take that, the payment is proportional to that. Now that's not based on any engineering ground. It's just an ad hoc fix. But it worked. So they weren't using real-time prices. They had some crude measure of wear and tear and incentivized production. Now it's a naive approach maybe. It's not trying to solve some social planet problem and prove a competitive equilibrium or something like that. It's an ad hoc technique to incentivize responsive generation. And guess what happened? It worked. So somebody commented that economists are bad at predicting the future. Well, no. They do a beautiful job when they do things correctly. So even though it wasn't the best way, if you look at the, from 2012, when they implemented this policy, to 2013, the availability fast generation in real time. So this is, I'm sorry, red is 2013, I made a mistake. So this, just look at real time. This real time generation and the amount of fast, very fast responsive resources that we need, it went up significantly since they implemented this rule. Okay? So it's not an efficient outcome. This is just a very recent report. But look at the resources they were able to get by putting in the right incentives, by recognizing what they needed. Okay. So anyway, so what if you did the real-time pricing mechanisms? That's what I wanted to say. What if we said we need real-time prices? Well, we can look at what an efficient outcome would look like in a competitive equilibrium model, and just use the fact that the cost of generation depends on G and G dot, generation and its derivative. It does. There's some sweet spot here. There's a speed and torque curve. for a gas turbine generator or a coal generator, and you'd like to be operating here. You don't want to bounce up all around the place. And so if you took a cost function that depended on generation and its derivative, what would you get? So say a separated function, a function of generation and its derivative. Well, you get the price is marginal value, of course. Okay. But the average price is average marginal cost. Any economist would agree. But look what's missing. So it was a Lagrangian relaxation of the initial condition to prove this. And if you move the initial condition along, the derivative is the same. So you lose anything here. So again, there's no equilibrium. Everyone goes out of business. So if you tried to use a competitive equilibrium analysis to set up this market, you'd get there's no equilibrium. Everyone dies. Okay. So competitive equilibrium would never compensate for wear and tear in a real-time setting. And the proof of this is very simple. It's not a deep result. I know I don't have much time, but so conclusions and suggestions. Yeah, I'm out of time. But so we have to finish this quiz. So I said the value, we could average this, look at the area under the curve. We've got the price, we've got the quantity. Is it true? I'd say yes. You're all wrong. It's correct. Electrons are electrons. Put them on the market and sell them. I think that's a valid answer. Another valid answer is it's false. Okay. There was a report in the Pacific Northwest that said the expected cost of oversupply is like $12 million per year, with 300 gigawatts of wind curtailment. So this volatility from this wind is actually a negative cost today. You know? And again, it's because there's no infrastructure to support the volatility. So if you had the infrastructure, the first answer is correct. If you had infrastructure to do with the volatility, it would be a correct answer to say it's $750 million. But because there's no infrastructure, it's a negative value. It completely depends on the infrastructure. Cars are worthless without roads. How about this? So this is basically a little perturbation of a huge load. So yes, 0. One correct answer is 0. This 800 megawatt perturbation of the 8 gigawatt load is something that you can just get rid of. You just basically, I'm going to use my lead lag controller in my control loop. Oh, that's right, I don't have a control system. I don't have the actuators to reject this disturbance. Oh, I don't have infrastructure? I was wrong. False. There's a disturbance to the grid. Maybe it's $500 million it's going to cost me. No, it's worse than that. That's false. This is the BPA regulation signal. This is what they send out to stabilize their grid. So the actual value is this. So this is the same day. You've got the wind generation in green here. You've got the load, which is fairly predictable. And so this is the entire Pacific Northwest regulation signal. So the actual value, I'd say, is the Seattle economy. Okay, if you didn't have this reliably, then the whole economy would collapse. It's gone. So its value is huge, even though it's 0 mean. All right, so just some extra credit points in case you missed this, in case you missed the other ones. I'll wrap up. Don't worry. What's the value of this? Suppose I can't deliver you this, but I can deliver you this. What's the value of this? Now, I'll tell you what it is. So I took this regulation signal and I put it through a high-pass filter so I could give it to Ivana in the Shetland Islands, who could ramp up and down her HVAC to cancel it out. Okay? So the value is a lot. I've got a resource there, and I can, I'm not the well, you're very cheap. So it's hard, isn't it? Actually, value. We know the value to the consumer is the Seattle economy, but this is very valuable, because I can take this and I can get it from HVAC, I can get it from gas turbine generators. That's through a high-pass filter. The remainder is this low-pass signal. So this plus this equals that. This I can pass on to the coal generators, So these guys are valuable as hell, And I take those together, and so I can divvy this up. And this is how I think we should think about ancillary service. There's a high-frequency component we can give to some resources, a low frequency we can give to others. But here's the joke. What's the value of that? Yeah, but it's not quite. And this is a subtlety. I just want to show how subtle value is. So if you look at this and this, there's a bit of an offset there. It's like a 10-minute delay. And if you control this, you say, well, the value is negative infinity. So even though it looks the same, these two products look the same. this would destroy the scale economy, and this one would absolutely regulate the grid. So the understanding of value, it's first of all, it's a trajectory, and there's so many subtle issues you have to take into account. And so you can imagine why I think real-time pricing is a huge mistake. Okay, so the power grid is a great playground for control theorists. We have all these fun toys to play with: batteries, capacitor banks, flywheels, pool pumps, and HVAC to regulate the grid. But we need these resources, and that's where economics is absolutely essential. Real-time markets, of course, have no value. I've been saying this for 10 years, and nobody's ever given me a scientific argument. And the empirical evidence says we cannot distinguish robbery from efficiency. Okay? So those plots are consistent with my efficient equilibrium, but they're also consistent with robbery. So it's a free market for firefighters. So this is a slide I used 3 years ago in this very spot. So why would we use them to control devices? And the EIA study shows there are alternatives. Now, what's remarkable is the start of this is this book by Fred Schweppe, Spot Pricing for Electricity, in 1988 is when the book came out. At the same time was this book by R. Coase in 1988. The two books came out at the same time. Now Fred Schweppe was in operations research at MIT. He was not an expert economist. And his book was actually fairly guarded, but the main message was spot prices to consumers to help to mitigate volatility. He was not naive. I mean, he did say that we should consider alternatives in the book. But Coase, if Schweppe had read Coase in the same year, he would have had written a very different book. Because, first of all, R. Coase, in his first chapter of his book, says, I never had a Coase theorem. It was a joke. Read this book. He says it was a joke. Samuelson called it the Coase theorem. But it says that if you had no ramping rates in a grid, no friction, if you could take power from Mumbai to India into London in a second, you wouldn't need anything but real-time markets. Yeah, Coase was joking. And he said that's why you need to take into account, that's why you have firms, you have dictatorships in a free market to deal with these transaction costs. So if Schweppe had read Coase, then he would have had a different story. And this lack of, what Coase says is that the divorce of the theory of economics from its subject matter, and the entities whose decisions economists are engaged in analyzing have not been made the subject of study, and in consequence lack any substance. And that's true for the real-time market. It's not true in other settings. But economists haven't bothered to understand lead-lag control, the impact of delay and loops, gain margins, phase margins. And I'm just saying all that. I'm joking. I don't know a lot of economics, but I'm just saying if we can't, this is going to happen if there's a lack of communication between the fields. So Coase was very angry at his result being called the Coase theorem, and this is a response to that anger. Okay. So I mean he's from the Austrian School of Economics. I mean he's considered a right-wing fundamentalist sort of economist, but he's still upset about this lack of communication. All right. So what do we need? Time of use pricing for peak shaving is valuable. Contracts for services, there's lots of success stories there. And there's an efficiency loss, but given the fact that I couldn't possibly define efficiency, I couldn't have defined efficiency for the flaps on the wings of an aircraft, and I couldn't do it in real-time control setting for the grid either. So we need smart appliances that facilitate these contracts, and we need control theory to make it work. And one thing the control engineers have to acknowledge is that no control engineer could stand up and say with a straight face, they know why the thing works. Nobody's ever solved the decentralized control problem. It's an open question in control, is how you can make local decisions in a networked system and have the overall system be stable. And it's been done through trial and error, really, to a large part in the power area. So if we redo everything, we don't know if we'll have the same robustness. So we need energy policy that's guided by physics and economics. So there should have been incentives for resources for ancillary service, not just wind farms. And that's enough. Thank you for your attention.
Sean, well, thank you. Excellent presentation and thought-provoking. I mean, unfortunately, David Newberry and Michael Pollitt are not in the audience because they're economists, so it would be nice to see
it's
them.
too bad, actually. I really would like to.
But I've dabbled a little bit into economics, and I read Fred Schweppe books, so if I could take, I'm an engineer, but I would take the economist.
All right.
Now I'd like to challenge you, basically, because the Fred Schweppe wrote that basically, fundamentally, you can break down price of electricity, spot price of electricity into 4 components, which is the energy price at the reference node. Second component is the congestion price. It means how to get power from reference nodes to wherever you want. So that's the locational value of electricity. The third is the loss component, and the fourth component is the ancillary services price, which is exactly what you're talking about. Now, the reason the current locational marginal price, which is in the PJM and other markets, does not contain the last component, which is the ancillary services, and Fred Schweppe made it clear that you need that price, is that there were little variations of the price of ancillary services around the average. So that means that utilities would contract for these ancillary services at the fixed price, and it was good enough back 20 years ago. Of course, now it is not the case, which means that the price for ancillary services is quite highly variable. So you have the point in saying that should be real-time price. So the value of the price for ancillary services shouldn't be contract based for whatever in time around the average, because that could be zero, but it should basically be also time varying. So I would challenge you and saying that it's basically the LMP. The reason LMP does not work in the current market setup is does not contain is a proxy and misses out the last component. So, for example, if you have a lot of wind on the system, then the average value of energy, which is the first component, would be zero, but because it is fluctuating, the value of the ancillary services will be very high. So basically, so what I'm saying is the market is incomplete, basically. It means it misses the last component, and I think you are right in saying that the spot price does not give you, because spot price is static. In your examples, you have basically you must have a component of a derivative, and derivative means it cannot be spot, because you have to look at time, what's happened before and what will happen later on. So you need a dynamic price with memory, which remembers what happened before and what is perhaps with prediction what will happen in the future. So although I agree with you, but I think you have misconstructed the economist argument that the proper price of electricity, as defined by Schweppe, is a proper one. It is just because of the past, the last component was averaged, while it should be perhaps variable.
So 2 points there. Okay. And so I did try to say that Schweppe really hedged in his book. He actually talks about contracting to consumers and so forth in his book, and it's people's interpretations later, that is a mistake. And so I won't mention names, but basically this has been taken. Schweppe's book, he's called St. Fred by many energy economists because he proposed the idea of spot prices. So yes, absolutely. Fred Schweppe was a visionary in some ways, but he was brand new, and so a lot of it's naive as well. But it's been taken to justify a lot of bad policy. So yes, thank you. That's really valuable. But the second point you made, I couldn't disagree with more. So I got caught right here. I was saying, as soon as I said that the value of the high frequency ancillary service was high, I realized, I failed my own quiz. So it's not that in real time. It's not. The fact is that when there's a scarcity, the price goes up. And that's a long-term investment problem to get these resources in play. And real-time prices, depending on energy and its derivative, are not going to give you those long-term signals. MISO, by giving at the end of each day a bulk payment, for the services provided, was able to get incentives like that, by not in real time saying up, down, up, down, up, down, but at the end of the day, looking at the services required, and what are they? Did you follow the regulation signal? Was there delay? Were you reliable? How much were you reliable? And you look at that over a time period, and you make a payment based on their services, and that is what given that that's the product. The consumer here is the control operator, really. What the product they need is a trajectory in time. So you've got to evaluate that, and it takes a day to look at that data, and then you pay based on the quality of the product delivered. And my stuff found that, like just like that, they could get incentives to get to the right product,
For intensive, you need long-term contracting, but basically, you need the reference price, and you get it from real-time pricing.
And I disagree.
Sean, a great lecture. I enjoyed it very much. And this issue of the spectrum between engineering and economics is something that arises in more and more of the very large-scale systems that get constructed in all sorts of different areas of the modern world. So trying to think about where the borderline is between the engineering and the economics is interesting. So one possible way to do it, this is the way I find quite helpful, is to think that while you call them Lagrange multipliers, they're fine. Right? So if you're doing an optimization problem, then naturally out of that optimization problem will come Lagrange multipliers. You may begin to call them shadow prices, and then you begin to run a risk. Because the problem arises when you begin to use the Lagrange multipliers as something in a context, in a game theoretic context, where there are incentives. While they're Lagrange multipliers, they can be quite easily turned into a decentralized control system with simply the instruction to all the players in the game, all the actors in the game, you act as a price taker. Right? You do not act manipulatively, you act as a price taker, because that will then cause the distributed control system to behave as the model is suggesting it should. And the difficulty is that as soon as you start to say, no, this shadow price will make a price, value, money, dollars will be transferred as a consequence of it, then the behavior of the actors deviates from the price-taking behavior, which is consistent with the overall optimization model, and becomes more strategic. And the problem then is that if you have something like real-time prices, all of the things the economists understand which make strategic behavior bad for a system all come into play. Because rather than a large economy with lots of actors, which looks like what generating and demand is, as soon as you differentiate it by minute or by second, it becomes a series of very small markets with lots of market power, which is local in space or local in time. Local in space because of transmission constraints, or in time because of blackout failures, forecast errors, whatever. So very large amounts of strategic behavior are incentivized. Now, how can you cope with that? How can you deal with that? Well, I guess then you have to understand the physics of the system. So where is value created by decentralized control? So one possibility is to say that you will allow behavior on the part of consumer households or Alcoa or whatever. You'll allow certain behavior which is subject to regulation, and that regulation is an attempt to make it almost price-taking. So the analogy here is that as the internet was developed, the congestion control mechanisms within it were mandated by the IETF, Internet Engineering Task Force, that the behavior that you can make the behavior of the application anything you liked, but it had to be TCP friendly. Now, what TCP friendly meant in economic terms was you can make it do all sorts of different things, but it has to carry on acting like a price taker. There aren't dollars being transferred here, but they are observing a Lagrange multiplier.
But this is beautifully you said this, because if you think about how I would like to evaluate and design a contract, then yes, I would do a simulation model maybe and look at these Lagrange multipliers, and then look at look at the prices that would be paid in this fictitious market, possibly. But remember that what I showed you there in my competitive equilibrium theory, that people would all go out of business.
Or because it depends whether, at the moment you have these spectacular risks, which as you described, you didn't absolutely say this, but I think it was implicit in what you were saying, that those prices are a consequence of strategic.
Oh, no.
I'll call it manipulative.
No, this result.
Strategic behavior.
No. This result is the average of P equals the average of the marginal cost plus 0. So this is the marginal cost of energy, but nothing for the deviations. This was in a competitive equilibrium setting. So this is a price-taking setting. So the Lagrange multipliers, it's very subtle.
So the huge risk that's attached there to that last term is a consequence of certain interaction. So here's a kind of question I ask. Suppose you said that if you have an appliance or you have a household or whatever, we have conditions. When you plug things into the mains, it has to stay within a certain voltage range, it has to stay within a certain constraints on inductance and this, that, and the other. For example, air conditioning systems or other systems, is it conceivable to imagine a regulatory mechanism for things that are on or off, for example, fridges or air conditioning, a regulatory mechanism that says you turn on and off and it should be sympathetic to the grid, sympathetic to the current.
That's being done today. That's being done all over the place today.
But if you make enough of the, well, I don't know the answer to this question, but the question is, are there simple, rather crude things that interact with, actually the second point I wanted to make, which is the following one, that if you think of this very large control system, distributed control system, then the sort of experience of the internet engineering kind of environment is that the analogy with an aeroplane is has drawbacks, because when you're designing an aeroplane, you know you've got two wings, you know you've got so many ailerons, you know the structure of this system you're controlling, and so you can put quite a lot of weight in, you can put quite a lot of effort into very sophisticated control schemes, because you know the design of the aeroplane. When you're designing the control schemes which have to go into all sorts of components, which will be plugged together in ways that you can't predict, then the control schemes have to be far cruder, because you want to assure stability under a topology which you don't know to begin with. And it may be, it's likely to be only possible to assure that stability if the control schemes are pretty crude.
Yes. That's what's done today. It's all very low gain feedback. I mean, that's the explanation. Sorry, but that's the explanation today. If you look at the way control designs are done, very low gain feedback. So they're very conservative. They're not, not the sort of, like you say, very sophisticated high gain feedback you have in an airplane.
But could we start this as the beginning of the discussion session
Oh,
to coffee? This would be a really useful place to start.
I would suggest to interrupt for 20 minutes or are there any short questions maybe, not comments, very short questions. Short comments. Otherwise we start.
That's
No, thank you.
Over coffee.